we're going to learn about greatest common factor. All right, let's take a look at the words in greatest common factor. First, we have greatest, which just simply means large, largest. Common, common, shared. The largest, shared, and then a factor. A factor, factors are whole numbers that divide evenly into another number. So I put 15 gumballs right here. So let's look at those and let's divide them evenly, okay? I can make groups of 5 gumballs. So I have 5 there, 5 here, and I can make a group right here. So that's 3 groups of 5. So whole numbers that divide evenly into another number. Well, we just took 15 and we divided it by 3 and we divided it by 5. So 3 and 5 are factors of 15 because I can multiply them to get 15. Or numbers you multiply. So factors are also numbers that you multiply. 3 times 5 are factors of 15 because we multiply them to get 15. We can also divide them evenly into 15. So factors are numbers that are divided evenly into another number or that you multiply to get that number. Factors are limited. It's important that you know factors are ending. There's only a certain number of factors for each number. For instance, the number 12. Okay, if I want to find the factors, I've got to break it down. So I'm going to break down the 12 into 6 and into 2. So I have 2, and now I'm going to take that 6, and I know that this is not a prime factor, and so I am going to break this number down until I have a prime factor. This is called a factorization tree, which we have seen in our prime factorization video, but there's a 3 and there's our 2, and so 3 times 2 is 6, times 2 more is 12, and so this is the prime factorization of 12, and these are all factors of 12. A factor tree can help us find the greatest common factor of a number or the largest factor of a number, but here's some factors, and here's 8, and I'm going to break 8 down into 4 and 2, and then I'm going to break the 4 down into 2 and 2. Okay, now these are just a few of the factors of the number 12, but these factors will help me find the largest factors that 12 and 8 have in common. Although 12, I know, is divisible by 1, it's divisible by 2, divisible by 3, divisible by 4, and 6, and 12. Okay, so 1, 2, 3, 4, 6, and 12 will all divide evenly into 12. Also, I can multiply these numbers to get 12. 1 times 12 is 12. 2 times 6 is 12. 3 times 4 is 12. So these are all of the factors of 12, and I can just list them here in a line. Okay, I'm going to do the same thing for 8. 1, I know, is 8 is divisible by 1, 2, 4, and 8. 1 times 8 is 8. 2 times 4 is 8. So these are all of the factors of 8. So I did break 8 down into a factorization tree and 12 down into a factorization tree. Now the purpose in doing that is to find the largest shared factor, the largest number that both 12 and 8 share. So let's see which one of these numbers is the largest that 8 and 12 both share. So they both share a 1, they both share a 2, so 2 is larger than 1. They don't both share a 3, but they do both share a 4. Let's looks like 4 is the largest number on the list. So it looks like 4 would be the greatest common factor. Now, breaking down the 12 and the 8 in a prime factorization tree, I can find 4 on the tree also. I see that 12 and 8, I'm just looking at the prime numbers, and I'm looking for which prime numbers that they both have in common. Well, they both have 2 2s on their tree. So I'm going to write down, I'm going to cross off a 2 each time I write it down. So there's 1 I crossed off of both trees. And here's another one that I'm crossing off of both trees. And that will give me what they both have in common, if I know what prime numbers they have in common. So it's 2 times 2 equals 4. What's the greatest common factor? Greatest common factor is the largest factor 2 or more numbers share. And 12 and 8 both share 4 as their greatest common factor. Okay, let's look at a real world scenario. Where would we ever use greatest common factor in the real world? Claire is making an emergency preparedness kit, or she's making several of them, kits, to share with friends. She has 12 bottles of water and 16 cans of food, which she would like to distribute equally among the kits with nothing left over. What is the greatest number of kits Mandy can make? So we're looking for the greatest number of kits she can make, and she wants to split everything up evenly, equally in each kit. She has 12 bottles of water, and she has 16 cans of food. And she's splitting the bottles of water and the cans of food up into groups. So if she's splitting something into groups, is our number going to be larger than 12 or larger than 16, or is it going to be smaller than 12 or smaller than 16? We're definitely looking for a smaller number than 12 or 16, okay? 12, I'm going to break down into a factor tree, and I'm going to find that it has 6 and 2 as a prime factor, and then 3 and 2 are prime factors. And I'm going to look at 16 and do the same. I'm breaking it down into 8 and 2. And then I'm going to break the 8 down into 4 and 2. And then the 4 is not prime, so I have to break that into 2 and 2 until all the way down until I have prime factors. Okay. So I'm looking at both of them, and I'm looking to see what they both have in common. They both have a 2 in common, and they both have another 2 in common. And I'm going to write down what they have in common one time. They have 1, 2, and then they have another 2. 2 times 2 equals 4. So that means Claire can make 4 kits. She can make 4 kits. And if she makes 4 kits, how many bottles of water would be in each kit? If she has 12 bottles of water and she's going to split them up into 4 kits, then there would be 3 waters in a kit. And how many cans of food? She would have 16 divided by 4, since she's splitting the 16 cans into 4 groups, and that would be 4 cans of food. Okay. Now, earlier on the last slide, I said that factors are limited. What I mean by that is that factors there's only a certain number of them. For the number 12, there's only 1, 2, 3, 4, 5, 6 factors. And for the number 8 here, there were only 4 factors. On this slide, for the number 12, it's the same amount of factors. For 16, we can list out the factors 1, 2, 4, 8, and 16. So it has 5 factors for 16. But each number has just a specific amount of factors, and that's all. It's not infinite. Okay, let's try factoring some numbers. Let's take a look at 8 and 15, okay? And let's factor 8 and 15 out. Let's break them down into prime numbers, and then let's find the greatest common factor of those two numbers, okay? Well, first of all, I could just list out the factors of 8 and 15. 8 has 1, it has 2, 4, and 8. 15 has 1, 3, 5, and 15. And so there's 4 factors of 15, and there's 4 factors of 8. So I'm looking at these factors, and the only factor I'm seeing in common is 1. Okay, let me try a factor tree just to make sure. We've got 4 and 2, and 2 and 2. Well, I know 2 doesn't go into 15. So I'm going to assume at this point that 1 is the only factor that they have in common. So their greatest common factor between 8 and 15 is 1. Well, that means that the two numbers are something called relatively prime. Relatively prime means the greatest common factor is 1 between the two numbers. Think of prime. Prime numbers got nobody but 1 in themselves. So prime means that that a number only has 2 factors, 1 in itself. Well, relatively prime, a relative is somebody you're related to. So that means that there's more than one person. Well, relatively prime, you can think that there's a relative, that this number has another friend, a family member, and they're relatively prime. So the only thing that they have in common is 1. It's 1. All right, so let's try number 2, 27 and 45. I'm going to break these down into a prime factorization tree. Actually, I'm going to go ahead and list the factors first. Sometimes listing the factors for larger numbers is not the best way to go, just because there are so many factors of a large number, and you're likely, the larger the number is, the more likely you are to miss some factors as you're trying to list them out. But I know 1 is a factor of 27. I know 3 is a factor because of my divisibility rules. I know that 9 is a factor. I know 27 is a factor. 1, 3, 9, and 27 are the factors for 27. So 27 has 4 factors. Let's try 45. I know 1 is a factor of 45. I know that 3 is a factor of 45. I know that 5. I know that 9 is a factor of 45. I know that 15 is a factor of 45. I know now that 45 is the factor of 45. So that's 1, 2, 3, 4, 5, 6 factors of 45. And I'm looking to see if they have any in common here on the factor tree. And right now, the only thing I'm seeing is 9. Well, let's see if I can find that same factor by breaking it down in a prime factorization tree and looking for their common prime numbers. Because like I said, the larger the number, the harder it is to find all of the factors of that number, and you may miss something. So a prime factorization tree is the best way, especially with larger numbers, to find the greatest common factor of the two numbers. You can't miss you can't miss all of the factors in a factor tree, but you can accidentally skip one if you're listing them out. So let's see, 9 times 3 and 3 times 3. And then for 45, we have 5 times 9 and 3 times 3. So I'm going to circle my prime numbers. And I have 2 3s in common on both trees. 3 times 3 is 9. So I only write what they have in common one time. And so their greatest common factor is 9. Okay, on this slide you are going to pause the video and you're going to try these out. You're going to find the greatest common factor in all 3 of these scenarios. All right, to find the greatest common factor of 49 and 21, I'm going to break this down into a factor tree. So I'm looking at 49. I'm going to ask myself, what number do I know goes into 49? Well, 7. And 7 times 7 is 49. So on my prime factorization tree, I have 2 7s. And for 21, I know that 7 times 3. And those are both prime numbers. And so looking at this tree, they only have one number in common, and their greatest common factor is 7. G, C, F, 7. Number 2, I have 13 and I have 32. Well, 13 only has 1 and 13 as factors. So 32 would have to have 13 as a factor, or the two numbers are going to be relatively prime. So let's try this one out. Let's see, it's 2 and 16. And 16 breaks into 4 and 4. And the 4s will break into 2 and 2. But they have nothing in common with 13. So I can say that 13 and 32 are relatively prime. All right, we have a word story. Number 3, Morgan is making goodie bags for her little cousin's birthday party. She wants to distribute the 28 candies and 44 whistles equally with none left. How many bags can she make? All right, so we're looking for bags. That means groupings. And we're looking for equal amounts and for nothing to be left over. So we have 28 candies and we have 44 whistles. So let's take those two numbers. Since we know we're looking for a grouping, and that tells me I'm looking for a smaller number, I'm going to be looking for the greatest common factor, the largest number that divides evenly into 28 and into 44. So I'm going to break these down into factor trees, find the prime numbers on both, and find what they have in common. Again, on this factor tree, they both have 2 2s in common. So I write down what they have in common only once, and I find that Morgan can make 4 goodie bags